Okay, good to go. Have a good session.
Okay, hello everyone. Welcome to the third day of TCC and Matches Made in Heaven workshop. It's my pleasure to introduce our first speaker of the day, David Woodruff from CMU. David actually, started out doing crypto, at least part-time. He worked on questions related to sublinear crypto, private information retrieval, sublinear secure computation, even things in crypto beyond sublinear. But now David is very well known as an algorithms person working mainly on questions related to streaming, sketching, sparse recovery, anything sublinear. And David, is recognized by quite a few awards, including the Pressburger Award and quite a few Best Paper Awards. And his talk today is actually in part based on a paper that just won the Best Paper Award at the Principle of Database Systems conference. So I'm really looking forward for the talk. The talk is on adversarially robust streaming algorithms. And thanks, David, and the virtual stage is yours.
Okay, yeah, thanks very much for the introduction, and thanks everyone for coming. So this is called Adversarially Robust Streaming Algorithms. It's based on two joint works, the first of which is with Omri Ben Eliezer, my student Raj Jairam, and Elan Yogev, and the second is based on work with my postdoc, Samson Joe. So this talk is about streaming algorithms and how to make them robust in the presence of an adversary. So to describe what that means, let me first go over the classic streaming model. So this is a model for capturing extremely large data sets. Some examples include internet traffic, financial transactions, sensor networks, and so on. And typically for these algorithms, you want them to make a single pass over the data set and be very low memory. So for an example, you can think of a router on a network with high-speed packets going through it, and it's hard to ask the internet to rewind itself. So the algorithm is inherently one pass, and these routers are typically very limited resource devices. In particular, they have a very small amount of memory. So a goal is to achieve one pass low memory algorithms. This is often formalized as follows. So in the streaming model, you have updates to an underlying vector x. Let's say x is n-dimensional. And x is initialized to all zeros. And at times t equals 1, 2, and so on, you receive updates of the form it, comma delta t, and this causes the change to the vector x, meaning that the ith coordinate of x should change from its old value by an additive delta t. Okay, so it indicates the coordinate, delta t indicates the change. And an important special case of this, which is how this model was originally introduced, is when all of these updates delta t are non-negative. And in this case, we call the model the insertion-only model. Okay, and yeah, so what we would like is at any point in time, the algorithm can compute or approximate some function of this underlying vector x using a small amount of memory. Some example functions that are well studied are the second frequency moment f sub 2, which is just the squared Euclidean norm of x, that is the sum of squares of entries of x. Another common example is f sub 0, which is the number of coordinates in x that are not equal to 0. Okay, so in this insertion-only model, f0 just corresponds to the number of distinct items you see in the stream. So you can imagine just seeing a stream of items, Each item corresponds to a coordinate of x. And at the end, you're just interested in how many coordinates of x are positive? What is the number of distinct items? Okay. And algorithms in the streaming model often store a small sketch or summary of what they've seen so far. And they do so in such a way that it's easy to maintain this sketch under these additive updates to the vector x. Okay, and typically you want much smaller than n bits of space. With close to n bits of space, you can actually maintain the whole vector x, and this is infeasible for large values of n. Okay, so just to go over a few example algorithms in the streaming model to give you some familiarity. The first is an algorithm for F2 estimation. Recall this is just for the sum of, F2 is the sum of squares of the entries of x. Now, often in streaming, it's hard to get exact answers. And so you need both randomization and approximation to get non-trivial space bounds for a large number of problems. So the way we relax this problem is we allow for outputting a relative error 1 plus or minus epsilon approximation, which I'm denoting here as F2 tilde, let's say with constant probability. Okay, so the following algorithm is due to Alain, Matthias, and Segedi. And the algorithm is very simple. So what it does is it chooses a random short and fat matrix S, where all the entries are plus or minus epsilon. So each entry is chosen to be with probably a half plus epsilon with probably a half minus epsilon. So I've drawn it here as epsilon times a sign matrix. By short and fat, what I mean is the number of rows of S is 1 over epsilon squared. Epsilon is your approximation parameter. The number of columns is n. And importantly, this matrix S, the entries can be 4-wise independent. This is important for streaming because it means that you can store S implicitly by just storing a hash function that can be specified with order log n bits. And whenever you need an entry in S, you just query the hash function. And another important property about this is that it's easy to maintain S times X in a stream. Okay, so S is a linear map. It doesn't depend on X. And so if I see an additive update to a coordinate of X, let's say the ith coordinate changes by an additive delta t, then it's easy to update my sketch. So my new value of my sketch is just my old value plus delta t times the ith column of S, right? You can think of taking X and adding a standard unit vector, which has the value delta t in the ith, a standard unit vector in the ith coordinate, and then you scale that by delta t. And when you multiply by S, this corresponds to taking the ith column of S and scaling it by delta t. Okay, so many streaming algorithms are linear. This is called oblivious, doesn't depend on X. Linear oblivious maps because they're easy to maintain. And what do you do if you want to estimate the F2 value, or the squared norm of X? Well, you just output the squared norm of S times X. Okay, and the fact that this works is a simple second moment argument. You can show that the squared norm of Sx is an unbiased estimator to the squared norm of X. And you can compute the variance. And the variance of this is order epsilon squared times the square of the expectation. By Chebyshev's inequality with constant probability, this gives a 1 plus or minus epsilon approximation. Okay, and the total memory is order log n over epsilon squared bits, right? So for each coordinate of S times X, I need order log n bits to maintain a counter, and I have 1 over epsilon squared coordinates. Okay, please stop me if there are any questions at any time. Okay, so these are, so that's a simple algorithm for F2 estimation. Let me also give you an example, the example of F0 estimation in insertion streams. So recall that F0 corresponds to estimating the number of non-zero coordinates of X, which is just the number of distinct elements in the stream. Again, we allow for 1 plus or minus epsilon approximation. And the way this algorithm works is as follows. This is not the most optimized algorithm, but it's a very simple and natural algorithm, we're going to choose a hash function h. It'll be a pairwise independent hash function. So again, low memory. It maps the numbers 1 through n, the integers, which are in correspondence with the n coordinates of x, to the range 0 through m of integers, where m is something like order n squared. Okay, so with good probability, you won't have any collisions under h. And the idea in the stream is just to maintain the smallest, roughly order 1 over epsilon squared hash values you see. So for each new stream item, you hash it, and you look at its value, and you maintain the smallest, more precisely, t equals 100 over epsilon squared hash values. Okay, and why does this work? Well, you can think of how many distinct hash values are you going to have. If you have f0 distinct items and with no collisions, you have f0 distinct numbers that you're throwing into this interval between 0 and m. And so where do you expect the smallest of these hash values to lie? Well, the smallest hash value should lie around the interval length divided by the number of hash values, which is m over f0. And so if I look at the tth smallest hash value, intuitively it should land around t times that value. So t times m over f0. Okay, and we choose t to be order 1 over epsilon squared so that this actually happens with good probability. It's fairly concentrated. And so if that's what's happening, then it's natural for your estimate just to be t times m divided by the value of the tth smallest hash value. And then this, you can show, is a 1 plus or minus epsilon approximation with good probability. Okay, so that's the whole algorithm. It's easy to maintain the smallest t values in a stream. And the amount of memory, well, yeah, you have order 1 over epsilon squared hash values that each take log n bits. So order 1 over epsilon squared log n bits of memory. This is an algorithm due to Bar-Yosef et al. This can be improved actually to order 1 over epsilon squared plus log n bits. This is an algorithm with Kane and Nelson. Okay, so you've seen a few streaming algorithms. I want to mention one thing is that these streaming algorithms, the way I've described them is they have constant success probability. If you'd like them to output a correct answer at every single point in the stream, and you have a stream of length poly n, the natural thing to do is just to independently repeat your algorithm order log n times, and then take the median of the estimates provided at each time. The error probability is now 1 over poly n, and you can union bound over the entire stream. That's one natural way of doing it. And for many algorithms, there are better ways of doing it. But, so this leads into the next thing I want to say, which is I want to talk about tracking algorithms. So it's often the case that you don't just want to output the value of the function at the end of the stream, but you'd like to continually monitor the value during the stream. So if we let xt be this underlying vector after seeing the first t updates of the stream, then you'd like your algorithm to be able to output a response rt at time t, which is within 1 plus or minus epsilon of the function value at time t. Okay, and we just saw how to do that at all times t by independent repetition. And pictorially, what this looks like is as follows. You can imagine the stream is sitting, maybe on some data center, which is generating the stream updates here. And here's your streaming algorithm on this being run on this computer. And I see an update, and I output a response. Okay, and this response, it doesn't go back to the data center. Okay, the data center that has the stream doesn't see this response. This is the standard model of streaming. And then the data center produces the next stream update. And I'm the streaming algorithm, I produce the next response, and so on. So perhaps surprisingly, the classic data stream model has assumed that the data stream is fixed before the algorithm starts, that future data does not depend on these responses, R of t, that the algorithm is outputting at these different times. but in many situations, you can argue that this is unrealistic. Okay, so oftentimes, future data does depend on past decisions. For example, if I'm monitoring a financial transaction stream, I might choose to make future financial transactions based on what I've seen so far, and these future transactions go into the stream. And so they depend on the output of my monitoring at previous time steps. And now there are no known guarantees for the streaming algorithm. It's unclear if they're still correct if my future queries can depend on the randomness of the streaming algorithm. And so this motivates us to define the notion of adversarial streams, where an adversary controls the stream updates. So what the adversary does is it sees these responses RT, and then it chooses the next stream update based on them. Okay, it doesn't have to be an adversary, but any agent that is making queries based on previous responses, we need algorithms that guarantee correctness in this situation. So you can model this by a bit of a different picture. So you have a two-player game where, again, I'm the streaming algorithm on this computer, and here is the adversary. And it generates this update I1 delta 1 to the stream. And then the difference now is that when I produce my response R1, this is fed into the adversary. Okay. And the adversary looks at this response, thinks a little bit about it, and then creates the second stream update. Okay. And then I create my second response, and adversary thinks about it, and so on. Okay, so this is the game that we're playing now that we allow the stream to depend on future responses. Yeah, so there's a question, does the adversary know the original X? So in the chat box, the adversary is creating the stream. Okay, so X is initialized to all zeros, and the adversary creates the stream. So the adversary does know the X that it's creating. Okay, and I'll describe more what the adversary's goal is in a moment. Okay, so the goal of the adversary is to make the algorithm fail to output an epsilon approximation. What do we mean by that? The adversary wants, at some time t, for the algorithm's response R of t to not equal 1 plus or minus epsilon f of xt. Okay, so it's feeding in updates and is trying to cause the streaming algorithm to fail. And for most of this talk, I'm going to assume that the adversary has unbounded computational power. So it knows the entire history of outputs of the streaming algorithm up to some time t. I will touch a little bit upon computational assumptions later. Okay, so what's one way of designing an algorithm that's robust, meaning correct in the presence of such an adversary? Well, one way is just to use a deterministic algorithm, right? Such deterministic algorithms are correct on all inputs, so it doesn't matter what the adversary chooses. However, in the case of streaming, for most problems, you actually can't get interesting memory bounds with deterministic algorithms. You can prove very strong lower bounds for deterministic streaming algorithms. And so you need your algorithm to be able to use randomness. So what are we going to do here? And I do want to emphasize that this is a real problem in the sense that you can take classical streaming algorithms. For example, this F2 sketch that I described earlier, due to Alon, Matthias, and Segedi, it's not adversarially robust. So if you remember, this was this short and fat sign matrix. And it turns out with a number of queries that is just proportional to the number of rows of that matrix, you can already cause the algorithm to fail. Okay, and even if the adversary is just choosing updates that are non-negative in this insertion-only model. So, the moral here is we need new algorithms. Okay. Okay. And the main result of this first paper with Ben Eliezer et al. is that we give two generic methods to transform any streaming algorithm A into an adversarially robust algorithm A prime with some space overhead, and I'll get into the details of that. So we call these two methods sketch switching and computation paths, and they are related to each other. But let me talk about these methods in more detail. Before doing so, let me just say that these methods have different advantages depending on what the underlying streaming algorithm you're starting with is. Okay, so sketch switching is particularly well suited if your underlying streaming algorithm is a very good tracker, meaning that, as I mentioned earlier, for some problems, there are algorithms where you don't have to just naively repeat the algorithm log n times at each time step and take the median to amplify probability to argue that you're correct on an entire stream. There are algorithms with better ways of doing that, and sketch switching is particularly suited for taking such a streaming algorithm and making it adversarially robust. Computation paths is particularly suited to algorithms that have a very good dependence on the failure probability delta. Okay, so and this is related to sketch switching, but I'm not going to get into the details because these are more streaming specific questions. But there are algorithms where if you look at the memory bound, there might be some term in the memory bound that doesn't depend on delta, and some other term in the memory bound that has a log 1 over delta dependence. And because of that, you can often get very small error probability for free. And if you have a good dependence on delta in your space complexity, this computation paths transformation is well suited for that. Okay, so yeah, so far this has been a bit high level, but let me just say the theorems that yeah, Salil.
Hi, David. I just wanted to ask a question about the model. So the distinction between the classic streaming model and the adversarial one feels reminiscent of things that I recall people studying online algorithms of different adversary models for online algorithms. I was wondering if you could just comment on that. Yeah. Am I remembering correctly, or is it different here in the streaming setting?
Well, I mean, the goal is somewhat different in online algorithms, right? Are you thinking about resource unconstrained online algorithms, those that just want to get a competitive ratio of?
Oh, no, that they talk about oblivious adversaries versus I forget what the term is for the non-oblivious adversaries. The oblivious ones don't know the randomness of the online algorithm or something.
I see. Yeah, we didn't really look into that just because a lot of that literature doesn't actually impose resource bounds on the algorithm, but right. It's a good connection, and maybe the terminology actually coincides here. I'm not sure. Yeah. Thanks.
And another question by Benny.
Does it help to assume that the adversarial stream has bounded memory? So meaning that the adversary is resource constrained. Is that correct?
Yes.
Yeah. So the results I'm going to present initially are information theoretic, so there's no assumption on the adversary. I will mention a computational result later in the talk.
Okay. I mean, if you start with your original motivation that suggests that the stream is so loud that we cannot work on it, maybe also it makes sense to assume that adversary cannot store all the stream, right? So
yeah, that's a good direction. Though you might want to give the adversary more power than the streaming algorithm. Sure. I don't know what the right model there is. Yeah. Thanks. Okay, so the main results here from sketch switching and computation paths. To describe them, I need to introduce a notion called the epsilon flip number. Okay, so if you have a function f, we can define the epsilon flip number, denoted lambda sub epsilon of f, to be the maximum number of times your function f is going to change by a multiplicative factor of 1 plus epsilon after seeing poly n stream updates. Okay, so just to give you some feeling for this, if I just have a counter in a stream, it starts at 0 and it ends at poly n, well, the number of times it changes by 1 plus epsilon factor, if I'm only seeing increments to the counter, is log base 1 plus epsilon of poly n. So this is order log n over epsilon. And in fact, for many problems in the insertion-only streaming model, the flip number is order 1 over epsilon log n. And we're going to focus on the insertion-only streaming model, so you can keep this number in mind. Just to see, for example, another well-studied problem in this model is the pth frequency moment, or the pth power of the p norm, just the sum of pth powers of absolute values of x. And the way I've been describing the model is the initial vector is the vector is initialized to 0, and at the end of a stream of poly n insertions to items, the p norm is also at most poly n. Okay, so the flip number, as I said, is log base 1 plus epsilon of poly n, order 1 over epsilon log n. Okay. Yeah, so let me say these two transformations in a little bit more detail, and then I'll get into proof outlines afterwards. So the idea behind the sketch switching transformation is we're going to maintain multiple independent sketches. Each of these sketches is good for tracking the function that we care about on a non-adaptive or oblivious stream. Okay, meaning that the stream doesn't depend on its randomness. We're going to start running each of these sketches at the beginning of the stream. We keep roughly flip number of these sketches concurrently. And the idea is we're going to slowly reveal information. When we reveal a piece of information about one of the sketches, we're going to immediately throw it away because its internal randomness has been compromised. Okay, so the idea is, the function gets initialized to, the function value at the beginning is 0. We initialize our response to 0. We start running all of our sketches on the stream. Okay, but we're only paying attention to the first sketch at the very beginning. And we look at the first sketch and we look at what it's estimating the current value of the function to be. But we're not posting this. Okay, we're not giving this to the adversary. We're still outputting this initial estimate 0, until at some point this first sketch is looking at its estimate and it says, oh, this estimate is not within 1 plus or minus epsilon of what was last posted to the adversary. At the very beginning, that would be 0. But in general, whatever was last posted to the adversary, the sketch sees that its estimate is not within 1 plus or minus epsilon of that, and says, uh-oh, I have to return something. So it's going to output its answer at that point. When it outputs its answer, the adversary sees it. Its internal randomness is compromised. We throw that sketch away, and we continue with the next sketch, S2, which has been running since the beginning of the stream. Okay, but now the adversary is going to start choosing its next queries, and its next query doesn't depend on any of the other sketches because it hasn't seen any information from these sketches yet. Okay, so I will get into this in more detail, but the idea is we're going to keep switching sketches, and once an estimate RT of some sketch SI changes by a 1 plus epsilon factor, we throw the sketch SI away and we start monitoring the estimate of SI plus 1. And at some point we decide to output the estimate of SI plus 1 as our response. Okay, but we continue outputting the old estimate until our estimate in SI plus 1 is no longer a good estimate to the function value. Okay, sorry, there's a question in the chat box. Oh, sorry. Okay, so yeah, that's the idea behind sketch switching that I'll get into more detail. The other transformation we have is what I called computation paths. And computation paths, what we do is we just have one sketch with very, very low error probability. Okay, so we're going to take our sketch and we're going to set the error probability. If we want overall error probability delta, we set the error probability to be delta times n to the minus flip number. And we're going to be doing the same thing that we're doing in the sketch switching paradigm. Namely, what we're doing is we output something, we give it to the adversary, and we continue using that output until our internal estimate says, oh, you know, that output is no longer a good estimate of the function value, at which point we're now going to post our new output. Okay, and then we're going to continue monitoring ourselves, and then at some point post a new output again. And what you can show is that you're only going to change the output roughly flip number of times. And since the stream is of length poly n, and you can assume that the output is order log n bits for all of these problems, what you can show is that there are only going to be n to the flip number of possible computation paths between the algorithm and the adversary, which means that the adversary is only going to be able to generate n to the flip number different possible streams to give to the streaming algorithm. And if you set your error probability delta prime to be small enough, you'll be able to union bound over all of these streams to guarantee correctness on any of them. Okay, so this is the high level idea behind both of these. Okay, so let me just say the theorems that are implied by these two transformations. So the first theorem corresponds to the sketch switching transformation, and it says that you take any algorithm A, which epsilon tracks f of xt, then you can transform it into an adversarially robust algorithm A prime, which epsilon tracks f of xt, where the space blows up by the flip number. Okay, so in the case of insertion only streams, this corresponds to a 1 over epsilon log n blow up in memory for many of these problems. And for the computation paths transformation, the theorem is as follows. You take an algorithm which is non-robust. It epsilon tracks f with probability 1 minus delta using space a comma delta. Then you can create an adversarially robust algorithm A prime that uses space a comma delta prime, where delta prime is delta times n to the minus flip number. Okay, so these are the resulting theorems that you get from these transformations. Okay, so there are some questions in the chat box. Maybe I'll. Okay, so it might be good to answer these as we're going in case they're sort of relevant to where I am. So one question is, the algorithm needs to keep some secret state of estimates. Is there any hope to avoid using a secret state? So the streaming algorithm needs to keep a sketch. There's some randomness associated with this sketch. That is sort of inherently necessary in the streaming model. I'm not sure if I understand the question completely. The second question is, would it be useful to output a differentially private average derived from the privately computed sketches? And the answer to that is yes. And there's follow-up work on that I'll get into later in the talk.
So can I just clarify the first question? So
yeah.
As I understood, you keep a bunch of estimates, but you only reveal some of them as you go to the adversary. You don't reveal all of them. So you still have something that you reveal and things that you do not. That's what I'm asking. Like, is there any simple or hard reason that if you reveal everything, then everything is impossible to be interesting?
Oh, yeah. So two things about that. You don't actually have to keep these estimates that you don't post. I mean, you just at a given time you check your estimate, and if it if it's far away from what you last posted, then you post it. Otherwise, you just throw it away. But of course, you still keep your sketch running on the stream. So there's no reason to keep those estimates around. The other part of your question is if you were to actually post all those estimates, then it's problematic, okay? Because then you could end up revealing a lot of information about your underlying sketch. Okay, so
you mean you don't need to store them, you can actually compute them as you need? or no?
That's right. So, for example, for this F2 estimation, what you'll do at a time step is compute the squared length of your sketch, S times X. You'll check if it's close to what you previously posted. If not, then you'll just, throw it away, and then, go on to the next update.
Got it. Thank you.
Yeah, sure.
Yeah, also a question by Evgeny in case, since
can you get the hybrid statement incorporating both of these two techniques? So it turns out that we're actually going to improve upon both of these. I'm not sure. Yeah, I mean, these things are related. It's just that there are some gaps in how streaming algorithms are constructed, actually. The way you get good trackers at all points in time versus the way you get high probability algorithms. So they're sort of useful in different settings. And I don't know of a sort of natural way of combining them, though I'll discuss follow-up work that does improve this later in the talk. Okay, so yeah, let me get into more detail here. So the first is sketch switching. I just put the theorem that you get here again. The blow up again is memory in terms of the flip number. And let me just apply it to one of the problems that we've seen, which is estimating the number of distinct elements. Okay, this F0. So there's a very nice algorithm due to Blasiuk, which is a tracking algorithm that shows how to use memory, which is log n over epsilon squared plus log n, and you're correct at all points in the stream. Okay, and you can see this is an example algorithm where you didn't just repeat the algorithm log n times. You would have had a higher memory if you were to do that. And just plugging this into our sketch switching framework, we get this blow up, this factor of log n over epsilon. But now we get an adversarially robust streaming algorithm. Okay, and in fact, you can optimize this log n factor a bit. You can replace it with log 1 over epsilon in this case. The reason is you don't really need to maintain log n over epsilon independent sketches from the beginning of the stream. You can instead maintain log 1 over epsilon independent sketches. And every time you throw away one of these sketches in the sketch switching framework, you initialize a new sketch. And you might be worrying, how can I initialize a new sketch at some point in the stream because it's missing this big prefix of the stream. But it turns out that the prefix of the stream that you've thrown away is only an epsilon fraction of the number of distinct items. So it's still perfectly good for estimation. So that's one way of optimizing this. Okay, so there are some questions. If you assume the existence of a random oracle, does it become easier to make sketches adversarially robust? Great question. I'll get into that later in the talk. Okay, so yeah. So sketch switching, what is the intuition behind this approach? So, the high level idea is the adversary wants to learn about your sketch and randomness to fool it. And what we're trying to do is carefully reveal information about our sketches. And as soon as we reveal any new information, we try to make this information irrelevant by throwing away our sketch. Okay, this is the high level idea. And here's the algorithm in more detail. There's another question. So you also assume that the adversary can't guess the sketch switch. So I'm not sure. So okay, so we have our sketches and we're just going through them in order. Okay, so when the first one posts, then we start looking at estimates of the second one. When that posts, we start looking at estimates of the third one. So your question might be more answered more clearly after I explain the sketch switching algorithm in detail on the next few slides. Let me do that now.
Okay, I was just thinking, if the adversary can guess, that you're switching, then he knows what information you have or what you don't,
So the switching is just told to the adversary, right? We post an output of a sketch, that sketch goes away, and the adversary knows that we switch. And if yeah, so the adversary knows when we switch sketches.
Okay.
Yeah. Okay. So here is the sketch switching algorithm in more detail. So we maintain k independent sketches, S1 through Sk. Each of these is a good tracker, meaning that it, in this case, is a 1 plus or minus epsilon over 10 approximation to the function value at all times of a non-adaptive stream. The number k here of independent sketches is roughly the flip number. So it's actually the flip number of epsilon over 12 of f. There's some epsilon fiddling here going on. I'll explain more where this comes from in a moment. The idea is, okay, so we're going to set this parameter I equals 1. What this means is we're currently monitoring the first sketch. Okay, and our initial output is 0, and that corresponds to just many of these functions evaluating to 0 when we initialize at the 0 vector. And here's the idea. So at time t, we have this sketch Si, right? At the beginning, I is 1, and so we're monitoring the output of S1. And if the estimate of Si is not within 1 plus or minus epsilon over 3 of the of what was output at the previous time step, then what we're going to do is, we're going to say, oh, the function value changed by a lot. So we're going to set our new output R of t to be the output estimate of Si, and we're going to throw away Si. And we're going to switch to start monitoring the next sketch. Okay, otherwise, our estimate Si is in this, is within 1 plus or minus epsilon over 3 of the previous response. And so we're just going to actually, at time t, we're going to output the same thing that the same answer that we did at the previous time step. Okay, and so let's try to understand this algorithm. Any questions about the algorithm? Okay, so let's try to understand this. So here is a proof outline for this algorithm. First, we note that we can assume the adversary is deterministic by averaging. Okay, so what do we have here in our model? We have two players. We have the streaming algorithm and we have the adversary, and they both might toss coins. Okay, and the goal of the adversary is to come up with a sequence of stream updates to fool the streaming algorithm. And if the adversary succeeds with good probability, then just by averaging, there's some fixing of its randomness, which succeeds with good probability. Okay, so we're going to assume that the adversary is deterministic. And what is this bias? Well, what this bias is this fixes the part of the stream that the adversary feeds into the ith sketch after the I minus first sketch returns some answer out. Okay, so we're running, we're currently monitoring the I minus first sketch, and the I minus first sketch said, oh, I need to post something, so it posts this output out. Okay, so the adversary sees this output out, and the adversary is deterministic, so it's going to keep seeing this output out. That's all it's going to keep seeing is out, 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 out until the ith sketch decides to post something. So, it just keeps seeing out. And so it's deterministic. It has some deterministic stream that it's feeding as its sequence of queries at that point. Now, this deterministic stream, it doesn't depend on Si yet, because none of the information that has been revealed to the adversary depends on Si. But the deterministic stream that the adversary chooses, it may depend on, all of the previous sketches, S1 through Si minus 1 that we've thrown out. Fine. But importantly, since this new deterministic stream that the adversary chooses doesn't depend on Si, Si is a good tracker. So it's going to be correct on all positions in this new stream. Okay. Now at some point, Si, so Si is just continuing to output this old value out until its local estimate out prime is not within 1 plus or minus epsilon over 3 of the output out. at which point we need to output out prime and switch to si plus 1. Okay, so you might worry here, well, the adversary is learning something about si, right? So, we've switched to si, and si hasn't outputted a new value yet. It's still outputting this old value, out, 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 out. So that means, oh, I learned something about the randomness of si. It hasn't outputted out prime yet. But remember that this stream that the adversary feeds after seeing the output of si minus 1 is just a deterministic stream. Okay, and si is correct at all positions in the stream until at some point it outputs out prime. And at that point we throw away si and move on to si plus 1. Okay, so
so David, so that's where I think where my question goes, right? Is that the adversary does learn about the switch, right? And so it knows about out and out prime, and you're saying that that's not a problem, right?
Yes. So what happens is it sees the output of the previous streaming algorithm,
right?
And it's going to keep seeing this output, right? So imagine what would the adversary query? It's deterministic. What would the adversary query if it keeps seeing out, 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 out? That's just some deterministic stream, right? Okay. So it comes up with that stream, and si. Well, we say si is this deterministic stream is independent of si. And so we just say that si is going to be correct on this, whatever deterministic stream the adversary were to choose, if it just kept seeing the output out forever.
Okay, that makes more sense. Thanks.
Okay, yeah. And at some point, si, actually changes that stream and says out prime. And at that point, si is not useful, and that's when we throw it away. Okay, so let me just remark a little bit on the epsilon twiddling here. It is important. So si is providing a 1 plus or minus epsilon over 10 approximation as a tracker, meaning on some stream that doesn't depend on its randomness, it's correct at every single point up to 1 plus or minus epsilon over 10. And this decision that we're making of whether or not we should output, post a new output, out prime, is whether or not out prime is outside of 1 plus or minus epsilon over 3 of the previous output. What you can show is, this is actually the case, that since si is providing such a good 1 plus or minus epsilon over 10 approximation, and the previous si minus 1 was providing a 1 plus or minus epsilon over 10 approximation, if you're actually outside of this range, then it means, well, actually the actual underlying function changed by 1 plus or minus epsilon over 12. Okay, the actual function value has to change by a lot to move you outside of this range. But the important thing here is this means that you can actually charge the number of times you change your sketch to the flip number of the function, right? Because if the function changes by this amount, well, that adds 1 to the flip number. So that's how we're able to charge the number of sketches we need to the flip number of the function. Conversely, what you have to show for correctness is that if the function f changes by a 1 plus or minus epsilon factor, then actually necessarily when you monitor si, its estimate out prime will have had to be outside of the range 1 plus or minus epsilon over 3 of the old output. So you're correct at all times. Okay, if the function moves around a lot, since these are providing you good approximations, your output must have moved out of this interval. Okay, so that explains the epsilons and the sketch switching proof. Okay. Okay, if there are no questions there, let me go on to the computation paths. So just to remind you, this other transformation we have is different. We just take any streaming algorithm and we just amplify its success probability. Okay, so let A be any algorithm which epsilon tracks a function with probability 1 minus delta, then the precise statement is, if that algorithm uses space L of epsilon delta, then there's a robust algorithm A prime that uses space L of epsilon over 10 delta prime, okay, where delta prime is the failure probability you want times n to the minus flip number. And, these sort of epsilon fiddlings are the same as they were before. Okay, so let's see a high-level proof for this transformation. Yeah, so all we're doing is saying, set the error probability to be really tiny. And the algorithm is going to be doing the same kind of monitoring that this sketch switching approach was doing. Okay, so it's going to post an output, and it's going to check, is this output, it's going to monitor its own estimate. And once its own estimate is outside of, let's say 1 plus or minus epsilon over 3 of the old output, then it's going to say, okay, well, then I'm going to have to post a new output, unfortunately. Otherwise, I'm going to keep using my old output as long as I can. And for the same reasons as before, you can show that, well, the output is only going to change flip number times. Okay. Now, what's happening here? Well, the stream is of length poly n by assumption, and we're assuming that the output can be represented with order log n bits, again by assumption. Now, remember, the adversary is deterministic. So it starts off, creating a stream that it's going to continue to use until you switch the initial answer from 0 to something else. And then you switch the answer, and then it creates a new deterministic stream that it continues using until you give a new answer, and so on. So you can think of this as like patching a bunch of streams together. And how many different streams can you patch together? Well, your output only changes flip number of times. You have a stream of length poly n. So this is poly n choose flip number of positions where you might change the output of the stream. When you change the output, you give a number which is specified with order log n bits, so it has poly n possibilities. Okay, so what you can think of as this sort of like big, I like to think of it as a tree or a decision tree. I mean, the adversary is creating these deterministic streams and stitching them together, and the number of possible streams that it could create is n to the flip number. Okay, just because of this counting argument that we just said. And because of that, if you set your error probability delta prime to be small enough, you can actually union bound over all of the adversary's deterministic streams, whichever one he ends up choosing based on your responses. Okay, so that's the idea behind computation paths. Oh, there's a question about assuming the adversary is deterministic. So remember, in our model, what we have is we have a two-player game with an algorithm that's randomized and an adversary that's randomized. And what the adversary is trying to do, the goal of the adversary is to try to feed in a stream that causes the algorithm to fail. And so, by sort of standard minimax type arguments, if on average the over the random coin tosses of the adversary it can fool the algorithm, then there's a fixing of its random string that fools the algorithm. Okay, so I hope that answers that question. So that's why we're assuming the algorithm is we can assume the adversary is deterministic. Yevgeny asks about practical use. So we haven't implemented these yet, so I don't know the answer to that question yet.
Actually, are there any practical attacks that are known? Like, were there any cases that of such adversarial, I don't know, maybe in context of polling or manipulating, tracking, ratings of TV, and any kind of practical context where adaptivity was used to?
Yeah, it's a good question. Like, if you can somehow maybe influence an estimate in practice, what's actually done. Yeah, so I don't know.
I guess
yeah.
in vote manipulation, right?
Yeah, no, I mean, that's
president
very timely
not
thing to
give
say.
idea. So let's.
Yeah, there's a follow-up question that says, what happens if we relax the constraint that it's not deterministic? Sorry, so I don't know if I was clear on the response to the earlier question. We do, the adversary is allowed to be randomized, but what you can do is argue that if there is a good randomized adversary, then by averaging, for one of its coin tosses, it has to be good. Then there's a good deterministic adversary, right? And then we show that we're ruling out deterministic adversaries by these arguments. So that's how we handle randomization in the adversary.
Yeah, like in crypto, if you have a PPT algorithm that inverts a one-way function, then you also have a circuit that inverts a deterministic circuit.
I guess he's only changing them during the flip, right? So he couldn't use the information he had. He's going to continue to produce that deterministic stream regardless.
Oh yeah, you mean so he's producing a deterministic stream. He's just seeing out, and
right.
Yeah. Sorry, there's another. Are these results tight regarding the amount of randomness? You mean yeah? So can we get tight bounds on the amount of randomness for the streaming algorithm? So we didn't look into that. We're very close to optimal space bounds. So this is like order log n bits of space for constant epsilon for many of these problems, and I think that should be close to randomness optimal, but I would have to think about it more. And for the particular problems, another question is: do these algorithms care that the stream is insertion only, or does it just matter to bound the flip numbers? Yeah, so far this has just been for flip numbers. Yeah, so this would have held for any stream and any problem with the given flip number. And let me just mention one comment on that. Sort of general streams where you can insert and delete as much as you want. For very simple functions, these have really high flip number, and so these would not be good algorithms. For insertion only streams, we saw a flip number of 1/epsilon log n. There's also a related notion called bounded deletion streams, where you're not allowed to delete too much, meaning that the function value can't suddenly drop very much in the stream. You can formalize it that it sort of never drops by a constant factor at any point in the stream, and those also have small flip number, and we get interesting algorithms in that case. Okay, another question is, what happens if we provide deliberately bad estimates to the adversary? Well, the goal here is you want to satisfy correctness. So, the estimates should be within the desired correctness range. So I'm not quite sure I understand the question. Another question is, can you get lower bounds in terms of flip number? Yeah, great question. Last slide of the talk, I'll get to that. Another question is, are there provable separations between standard and adversarially robust streaming? How big are the gaps? So what you're going to see is actually we have follow-up work that for insertion only streams gives nearly tight bounds. Essentially tight bounds for these problems. For streams with deletions, I don't know, that's also an open question. Okay, so let me just get back to the slides here. So this was the computation paths high-level proof. And you can apply this to a number of different streaming problems. These are the results that we obtained in this initial paper. I'm instantiating it with the flip number being 1/epsilon log n, as it is for insertion streams. And you can see that, for things like F0 that we looked at, number of distinct elements, the blowup is from 1/epsilon squared to, 1/epsilon cubed. And for FP estimation, which includes F2 that we talked about, from 1/epsilon squared to 1/epsilon cubed. Okay, and I won't get into the details of the other problems. Some use sketch switching, some use computation paths. But yeah, there are many streaming problems that we cover. And I do want to talk a little bit about a question that came up, which is computationally bounded adversaries and cryptographic assumptions. So we were able to, in this initial paper, improve this 1 over epsilon cubed dependence for a number of distinct elements to 1 over epsilon squared, which is optimal even with no adversary. But then in follow-up work, we actually got an information theoretic improvement, meaning that we could get this bound without this. But still, I think it's worth presenting how computational assumptions might naturally fit in here. So let's look at polynomially bounded adversaries and recall this non-robust F0 algorithm. Okay, this was a super simple algorithm. We just had a hash function. It was pairwise independent from the indices 1 through n to a range of size order n squared. And the algorithm, all it did was maintain the order 1 over epsilon squared smallest hash values that it saw in the stream. Okay, that's the algorithm's state. And so, like you look at this and you say, well, if I'm an adversary and I want to break this, would it ever make sense to insert the same item twice in the stream? No, it wouldn't, because the state of the underlying streaming algorithm remains exactly the same if you insert the same item twice. Okay, so you can think of what the adversary is doing without loss of generality is inserting a sequence of distinct items, and really breaking this algorithm comes down to breaking the hash function h. Okay, so in a random oracle model, you can't break this algorithm. You guys know this much better than I do, but what you can assume here is if you make the assumption of exponentially secure pseudo-random functions, which in practice could be AES or SHA-256. So here is the assumption that we would need is for any constant c greater than 0, there's a constant d greater than 0 that may depend on c, and a small family of hash functions, n to the d hash functions that can be stored and evaluated in a small amount of memory. We want to order log n bits of memory, such that any n to the c time adversary does not get a significant advantage in predicting the values of these hash functions. And if you can't break this hash function, you won't fool the state of this algorithm. And so that's a simple application where you don't need these generic transforms, sketch switching computation paths. You just need really to have a random oracle. Yeah, okay. But as I said, we actually improved this. Oh, sorry, there's a question. Yeah, the dependence is very strong. The assumption is very strong. I mean, I think this is like the strongest assumption you can make. But you can make weaker assumptions, and then you pay for it in how big your hash family is, how much memory it takes to store a function in that family, and so on. But if you make the strongest possible assumptions, then that are still consistent with what we know, I think you can get order log n bits of memory here. Okay, so okay, yeah. Let me just get into follow-up work. Sorry, I'm going over time. So follow-up work, yeah, going back to a question, there's a very nice work of Hasidim, Kaplan, Mansur, Matthias, and Stemmer, which does show how to use differential privacy in this setting, which is really a very nice application of differential privacy to data streams, a very novel one. And applying it in our setting, this would improve our bounds in this original paper from 1 over epsilon cubed to 1 over epsilon to the 2.5, okay, up to log factors, for the examples I mentioned and for many other streaming tasks. And very recent work with Joe, which I just posted on the archive a few days ago, we actually give a a different technique called difference estimators. So we actually don't use differential privacy. We use a new streaming technique, which improves the bounds of 1 over epsilon cubed in this first paper and 1 over epsilon the 2.5 in the second paper to get an optimal 1 over epsilon squared dependence for number of distinct elements, F2, and many other streaming tasks. I do want to mention this is optimal in the sense that there are actually lower bounds for non-robust algorithms that scale as 1 over epsilon squared. Okay, so these techniques, they go through what I'm going to call a difference estimator. And let me just quickly motivate what those are. So, here's the motivating question. Going back to sketch switching, when we switch our sketch, we do this whenever the output changes by a 1 plus epsilon factor. And, the question is, do you really need to switch your sketch every time the output changes by a 1 plus epsilon factor? And, the answer to this is, well, maybe. I mean, it's unclear what the adversary is learning in general. So let me refine this question and say, well, okay, if the last output out was a 1 plus or minus epsilon approximation to some function value f of x, and f of x, changes by a little bit. So you're in the insertion only model, you insert some additional elements, you get a vector x prime, and you look at f of x prime, and f of x prime is not much larger than f of x, okay? So let's say it's at most 1 plus order epsilon times f of x. The natural question is, do you really need a brand new 1 plus or minus epsilon approximation to f of x prime? It seems wasteful, right? You've already posted the old output and given it to the adversary, and maybe you can actually use that output for something, interesting, for something useful. And that motivates the notion that we introduce of a difference estimator. So the idea is, well, maybe we can try to approximate the difference with a sketch, f of x prime minus f of x. And, this difference, well, sort of by assumption, if f of x prime is, only 1 plus order epsilon times f of x, then this difference is very small. So, if we could approximate this difference only up to a constant factor, then we could take that approximation and add it to out, this output that we already produced, which is supposed to approximate f of x. Why don't we, we posted the thing, so why don't we actually use it? We take what we posted and we add our difference to that. And, they add up, without any errors, they would add up to the new function value. But, the motivation here is, well, maybe I can approximate this difference much more efficiently in a stream. There's a question here. Okay, let me get back to that question because it's not directly related to what I'm saying right now, but I'll get to it in a moment. And so, yeah, so we need to approximate this difference up to some additive error epsilon f of x under the promise that, the difference is small. I mean, in general, you need more than this, but this is sort of where you should start thinking. And it turns out that, surprisingly, there aren't streaming algorithms that exist to do this. So, how might you imagine doing this? Well, you could imagine separately approximating f of x prime and f of x each up to 1 plus or minus epsilon, and then just, taking the difference yourself. But, then you're going back to this, first paper that we had, and the complexity is too high. The memory is too high. And it does seem like it's overkill because you're estimating both of these with very good accuracy. Alternatively, you could imagine estimating both of these up to a relative constant factor. But that's no good either because, when you subtract these two things, the error can be order 1 times f of x. So, you really need something new here. You need some way of estimating the difference to get this kind of additive error. And, that's exactly what we design in this paper for a number of different streaming problems. And, just to give you a very quick example, for the squared 2 norm, if this is your new vector and this is your old vector, and you're looking at the square difference, then you can write it using Pythagorean theorem as the squared length of the difference vector plus twice the dot product of the difference vector and x, whatever. But the point is, when you write it like this, you can use the fact that you can show that this difference vector has a small norm under this assumption. And because of that, for this, you can just use an F2 sketch with a much poorer accuracy. Okay, and there are also streaming algorithms for estimating a dot product, which you can afford to do with very poor accuracy. Okay, so that's the basic idea, and you can show that you only need 1/epsilon memory to estimate the difference with this guarantee. Okay, so that's the motivation, and we have this general framework that we call sketch stitching and granularity changing. And just to say it, if x is the current underlying vector, the idea is, okay, well, x, at some point it's going to grow to some new vector x prime when you insert a lot of stuff, and the function value might change by a factor of 2. But in order for that to happen, at some intermediate point, it has to change by 1 plus epsilon. This intermediate point I'm calling x1. And so, why don't I try to approximate this difference, f of x1 minus f of x? And I can use, a much smaller memory to do this. It turns out that, constant factor, or more relative error, or more technically constant factor over log 1/epsilon suffices for this difference. What's going to happen is then you're at x1 and it grows to a vector x2, and f of x2 is like roughly 1 plus 2 epsilon, the original function value. And now the difference is larger, so you need to approximate the difference with an even smaller relative error. And it's important here that you actually approximate this difference as opposed to just the successive differences, because for each one of these are getting additive error order epsilon f of x. If you added them all together, you'd get about order 1/epsilon of these, and overall you'd get f of x error. So instead we move up one level in the binary tree you can think of. But then if we want to then x2 is going to grow to a vector x3, and we're going to have this happen. But now we can use successive differences. So we can approximate the difference from f of x to x2 using what we previously posted to the adversary. And then we can approximate the difference of x2 to the next vector using what we posted to the adversary here. And this is high level, but I just wanted to say that the additive errors add up over log 1/epsilon differences in a binary tree representation of what happens when you grow a vector x to x prime. So you end up adding up all these difference estimators at different granularities, and you get the overall additive error that you desire. So let me just say one more slide on this and then conclude. So there's a trade-off here. So for this F2 example, at the top level of this binary tree, we have log 1/epsilon levels. At the top level, we need to use a lot of memory, like 1/epsilon squared memory. We need very fine estimates, but we only need to sketch switch order log n times. And at the bottom level, we need 1/epsilon memory in each of our sketches, but which is much smaller, but we need to sketch switch more often, 1/epsilon times between these difference estimators. Balancing everything together, we can get an overall tight optimal bound for this problem. So let me just conclude with open questions. A question that came up by you guys is, if I have general streams with positive and negative updates, can you prove strong lower bounds? So that's an open question. And a more precise statement of that question could be to look directly at the optimality of flip number dependence. Okay, so what this follow-up work that I just described gives is a dependence on the flip number, which is epsilon times the flip number. That's the blow-up. Or yeah, and more precisely the max of this and 1. This ends up giving us optimal bounds for insertion-only streams. And it improves the original flip number blowup in this first paper that I described. Now, this follow-up work using differential privacy of Hasidim et al. Gets a flip number blowup, which is square root flip number times log n. Okay, so this ends up dominating our new flip number dependence when the flip number is larger than log squared n over epsilon squared. Okay, now for insertion only streams, the flip number is log n over epsilon, so it's not as useful there. But you could imagine for streams with positive and negative updates for some functions, if you have a very large flip number, then the square root flip number dependence is well suited for that. And so natural question is, combining these techniques, is it possible to understand what the tight dependence on the flip number is in all cases? And yeah, just I want to just say that, ask, are there other uses of cryptography for data streams? So I feel like there's a nice interaction between these areas, and let me just stop there. Thank you.
Okay, thanks a lot, David. There was a lot of interaction during your talk, and I guess we've almost exhausted our time slot. So I think there are still a couple of questions, one about short-term quantum computer, the other by Frank. But I think that, yeah, so if David, if you have quick answers, maybe.
Answers. Considering online algorithms you are serving have limited memory, do you think there's a potential for a quantum version of them on limited memory short-term quantum computers? I don't know. That's a good question. Yeah. Did you have some more specific version of that question, Mostafa? Okay.
Yes, I'm with you.
Yeah, I'm not sure I really understand the question.
Well, considering that we are limited on memory, I've been wondering whether there are applications to quantum computers, as so far they are limited. We are limited on the qubits, which are somehow practically or physically stable. So are there some connections, I've been wondering, to quantum computing?
I'm not sure. I mean, I have seen, I think, maybe 1 or 2 papers that look at quantum computing in the streaming model. If you want to just, look at quantum computing by itself without being in the streaming model, yeah, I mean, if you have ways of, a low memory algorithm that has ways of maintaining its state under these updates, you might be able to transfer some of these results. I don't know. Yeah, it's a good question. Okay, the last question is, Frank mentioned that it is difficult to say what the adversary is learning, although can we assume that the adversary is possibly learning something about the function?
Something's gnawing at me, David, is to make sure that when you do that flips or something, the adversary is learning something, must be learning something, I think.
Well, yeah, I mean, what is you mean when you switch to a new sketch and you have this deterministic stream? I mean, it's learning that the output hasn't caused it to change. Is that what the randomness hasn't caused changes to change so far? Yeah, it does learn that, but the algorithm is still correct on the stream because it was chosen deterministically beforehand. For some of these attacks, like the attack I mentioned on the AMS sketch, you can kind of feed in an input, look at the squared length of the sketch, and you can kind of ask, well, in this case where you had this random sign matrix, some columns are more correlated with each other than other columns. So you can kind of, try to, focus your queries on columns that, cause non-random correlations, right? Like if I keep choosing columns that have a dot product that are biased positively towards each other, then or negatively, I can very quickly fool the sketch. So that's kind of what you use in these adversarial attacks.
Yeah, just kind of masking the what you're leaking, right? And so that the adversary can't guess. And I like that your approach you just made. So
yeah. I mean, yeah. So that's why we needed these frameworks. Yeah.
Okay,
so David, maybe a very quick question, just like 1 second question. I'm just curious. This is like fascinating stuff. What do people use, I guess, in practice? I guess I know hyperlog log, which is similar to one of the schemes that you presented. So what do people use in practice, for example, for estimating number of distinct elements? Because I imagine it's very super practical stuff. Any of the stuff made it to practice?
Yeah, so the people actually do use hyperlog log in practice, which is better than what I presented here. What I presented here was 1 over epsilon squared log n bits of memory. Hyperlog log is 1 over epsilon squared times log n bits of memory. You can actually further improve that in theory, though that hasn't been practically adopted. I think another interesting direction is just making algorithms that people already use in practice private in sort of the most practical way, even if those are not the most optimal from a theory standpoint. Hyperlog log, all it's doing is so to say it quickly, it subsamples at multiple scales and hashes items into buckets. And so actually all it's doing is, hashing items. And you can use this same, and we do this in the paper, the same random oracle assumption or, strong pseudo-random function assumption to design an adversarially robust algorithm in that setting. I think a nice open question is to take other simple algorithms in practice and see where you can just plug in crypto to make them adversarially robust.
But for now, basically, you're saying hyperlog log is state of the art in practice. For now, at least, none of the theory made it yet.
For F0 estimation, non-robust streams, I mean, that's what's in practice. Hyperlog log is what people use all over the place. Yeah.
Thank you.
Sure.
okay, so thanks a lot, David, and and of course, if there are further questions, I'm sure David will be happy to answer offline. It's been a very interactive talk and very, very interesting, David. Thanks a lot, and see you all at TCC in half an hour.
Thank you, David.
Yeah.
Thank you, everybody.